Hey everyone. In this edition of ITS Now, we'll be looking at a paper I gave at the 2022 TRAFEX conference. It's titled Making ITS Equipment Resilient to Extreme and Changing Weather Conditions. So it'll be looking at what we need to be thinking about when we design and specify ITS installations, thinking about how the changing technology landscape will affect what we're doing given the context of the climate emergency and the need to reduce carbon in everything we do. I'm Alistair, and this is ITS Now. We are now witnessing the effect that global warming is having on the environment, with very diverse climatic events impacting the daily lives of people around the world. I will be examining the issues posed by the climate emergency for the deployment and operation of ITS equipment, with particular focus on the following areas: appropriateness of traditional ITS platforms and equipment in a changing technology climate, carbon reduction in the construction and operation of equipment, and resilience to extreme natural events. I think it's fair to say that some natural events are probably not economic to engineer mitigation features for. However, whatever we do, we need to consider some basic issues to try to reduce the impact of these issues. Some might say that we aren't actually affected by these events, but this sort of scene is becoming increasingly familiar to many. We've seen many instances in recent years of flooding events. This example of a National Highways new smart canal gives an indication of how technology installations could easily become compromised. Although we might not have to face this on our morning commute regularly, this example from Auckland, where the motorway was inundated by the sea, shows that we need to have awareness of these issues when we're designing where we want to install technology assets. And although many flooding events are very localized, this will not help if equipment is located in a low point. This is a great example of a traffic signal installation operating despite the level of water. The center of the push button should be a meter above the footway. So this shows there's at least 800 millimeters of water at this point. In these older style poles, the electrical terminations are carried out at the top of the pole. So these are well away from the water at this point. However, I wonder where the traffic signal cabinet and electrical feeder pillar are. I can only guess that these must have been uphill of this. We might feel that snow won't cause much of an issue to ITS installations. An unintended consequence of changing to LED traffic signals in locations which get significant snowfalls is the fact that the halogen bulbs in older installations used to melt the snow on the signal heads, maintaining visibility. But the new heads don't get warm enough to do this, resulting in a requirement to manually clear them in some locations. And in these conditions, if equipment needs maintenance activities to be carried out, it can not only be difficult to get to the locations, but it may also not be a safe thing to open cabinets in these poor weather conditions. In a lot of locations, dust storms are increasingly causing problems, which, like snow, can make undertaking maintenance activities both difficult and dangerous. But in these locations, heat is the main issue that needs to be mitigated against. Flood gauges in this picture shows that fire isn't the only issue to be faced in some locations. The extremes in weather is causing us to need to face a multitude of scenarios when designing ITS installations. Even though many highway corridors in areas where bush-type fires are more likely to occur often deliberately have little vegetation near to the carriageway, the transmission path for these events can result in devastation for vehicles and equipment. I'm also always amazed, though, how often drivers seem to stop under bridges or gantry structures when there is a vehicle fire. In this example, the impact of high winds on these vehicles on a bridge is clear, and at least the weather sensors on the right have stood up to this without apparent issue. However, the design of some ITS features does need to consider how it will stand up to wind and storms. This American example shows the pitfalls of using overhead catenary wires to mount equipment on in this situation. And we can even face issues in this country, as this temporary base shows in Scotland. One of the most devastating issues we do have to face is lightning. This is reportedly the damage caused to the carriageway in a Portsmouth residential street, having been struck by lightning. It appears to be centered on an access chamber, so utilities could have been damaged by this event. We're probably all aware of the issues of lightning striking overhead structures. But in locations like Sao Paulo in Brazil, which has a very high incidence of lightning strikes, a lot of the electrical and communication circuits are carried on overhead cables, making any equipment connected to these highly vulnerable to damage during the nightly electrical storms which occur there. There are many great examples of new technologies and equipment emerging from suppliers, which I would encourage you to explore and look at with a change in perspective, not to just keep doing business as usual, but to look at how we can encourage our clients and supply chain to adapt to the requirements for new approaches, which will meet both the requirements to tackle the impact we have on the environment, but also to link to the overall evolving technology landscape, which is in itself undergoing a huge step change. We're currently experiencing the start of a pivotal change in technology use within the transportation sphere, so much so that the use of the term mobility is now universally used to denote the way in which multiple modes of transport and technology can be used to provide enhanced experiences for users by using data extracted from a huge array of sources. This integration of information and movement characterize the increasingly data-centric reliance of our general lives, as well as the way in which we move around. Because of this, the operation of our streets and highways, which in many areas have been at the forefront of technology adoption to manage traffic flow over the years, will need to make a huge change to be relevant as vehicle technologies and wider online applications come to the fore. Traditional intelligent transport systems deployments have largely followed a top-down heavy engineering model, where a traffic authority will build a centralized system to provide a predetermined set of operational features and capabilities. These systems typically use information from inputs which are specifically provided for a task, then provide outputs which use built features to achieve the required outcomes. So, as an example, early traffic signal installations used vehicle detectors to provide the roadside traffic signal controller information about the traffic on each approach to a junction, which allowed the signals to respond flexibly to meet the current demand. However, these couldn't coordinate with other junctions or make use of information from other sources to best optimize their operation. So to overcome this, Most cities installed urban traffic control systems to achieve a more holistic approach to traffic control. And over the years, these systems have become increasingly sophisticated and able to communicate with wider and wider types of infrastructure. However, in the same way as with those early sets of isolated traffic signals, our modern day traffic systems will need to respond to the needs and expectations of new requirements and be more capable of operating with less centralized systems topographies as part of a much wider overall technology landscape.
Please remember to click on the like and subscribe to keep updated about ITS Now.
Although there has been much speculation about the way in which automated vehicles will impact the architecture and operation of intelligent transport systems, the introduction of connected vehicles in significant quantities will actually inevitably impose a significant change to how we currently manage and operate our highways. And subsequently, the ITS infrastructure will need to respond to this. Because of this, much of the heavy engineering solutions we are currently installing are likely to become obsolete before we would have expected these installations to have become life expired. Our normal expectation is for equipment to last 15 years or more, but there are huge numbers of installations of all sorts of traffic installations which are in excess of 25 years out on the network. I think this illustrates the enormity of the task which we are going to face over the coming years to be able to upgrade or replace equipment in the most appropriate way to respond both to the increased pace of technology change and to reduce their ongoing impact on the environment. So, my takeaway number one: our traditional engineering mindset of building longevity into every element of what we install will need to change to achieving this as part of a system of systems rather than for each individual piece of equipment. So instead of building things that Brunel would have been proud of, we need to achieve reliance with systematic implementations rather than relying on individual elements. When we look at modern intelligent transport systems, we see that most types of equipment now use modern, energy-efficient electronic components that significantly reduces the amount of power which they consume when operating. So that as designers and operators of these systems, we probably feel that we have made major strides in achieving carbon reductions in our strive to protect the environment. However, many modern intelligent transport systems deployments actually consist of huge engineering construction projects to achieve the benefits of the technology deployments. Major civils, structural, and geotechnical schemes are often required to mount equipment on. As an example, these full-span motorway accessible gantries are in themselves significant engineering installations. When you whiz past these structures at 60 to 70 miles an hour, most users will not really be aware of their sheer size. It is only when you get inside them that you really appreciate what they amount to. Now, obviously, these structures use a lot of energy to manufacture them, to construct and install their various elements, and to maintain over their life cycle. So what we really need to do is to review the requirement for these installations in the first place, especially given the context of the overall changes to the technology landscape, which we're now starting to experience in intelligent transport systems. So my takeaway number two: over the coming years, as we move towards the adoption of new technologies, we need to ensure that whatever we build today will be of the most benefit in the longer term in order to reduce waste by adapting installations in the future for new purposes. Although the above ground structures in intelligent transport systems deployments are probably the most obvious candidates for review when looking at how next generation equipment should be constructed, many installations currently use extensive subsurface networks of ducts and access chambers to provide data and power connections. As equipment continues to become ever more efficient, as an example, a decade ago, the majority of installed traffic signals still use 50-watt halogen bulbs in the signal heads. And although the move to LED light sources brought significant energy reductions, further technology developments have gone even further to produce a new 1-watt traffic signal head. When these continuing developments are combined with items such as micro power generation, we've seen the output from photovoltaic panels improve over the years, and then new developments such as the vertical turbine designed to be installed around columns in the roadside, which is turned as much by turbulent air from passing vehicles as from the wind. Then combine these with developments in battery storage of energy. The requirements for mains electrical connections will inevitably be reduced for many types of installations. In addition, the use of low-powered wireless networks provides an opportunity to step away from fixed communications networks for many applications, making the installation of equipment much more flexible because they will not be detected by the availability of fixed power and communications connections. With the increasing capacity and speed of cellular network, even CCTV can now often be used without the need for hardwired data connections. At the same time, existing duct networks could be repurposed to provide more high-capacity strategic communications networks, such as fiber optic backbones. These existing traffic systems duct networks across our urban and interurban routes could therefore provide a valuable way in which to increase the capacity and reach for communications infrastructure. As the development of connected vehicles progresses, the need for many roadside intelligent transport systems equipment will diminish. The range of services that will be provided to drivers by vehicle-to-infrastructure and vehicle-to-everything capabilities of connected vehicles will probably see the gradual demise for a broad range of equipment, including some data gathering used for traffic flow, journey time information and incident detection, variable message signs, etc., because drivers will be provided with information directly on their in-vehicle displays, and vehicles will also provide data back to highway authorities on a range of parameters that will do away with the need for much of the vehicle detection infrastructure which currently exists. This last element currently costs authorities huge sums to maintain loops and above-ground detectors, and would drastically reduce the amount of civils infrastructure maintenance activities associated with this element of the sector. So takeaway number 3. We know that we're on the cusp of a major technology shift. We also know that post-COVID, the change to newer generations of vehicles is faster than predicted even a couple of years ago. Then put this in the context of the climate emergency, and we see that there is a real need to modernize our intelligent transport systems infrastructure at pace. But the budgetary restraints that exist for highway authorities results in it being difficult to undertake standard maintenance, let alone undertaking the biggest change to how we manage traffic in the last couple of generations. So how should we evolve the design of ITS infrastructure to cope with both the changing technology landscape, but also to respond effectively to the climate emergency and the ever-worsening natural events that this equipment will need to withstand? Ofgem CEO Jonathan Brearley is reported to have recently commented on power utilities' response to Storm Arwen last year, that the frequency of extreme weather events was only set to increase. So it was really important that industry and those involved more widely learn from Storm Arwen to better respond in future. So what mitigation actions can we take to overcome some of these problems? The location we choose to install equipment is a key element. This example shows cabinets that were placed on a small bank to overcome an occasional localized flooding issue. In addition to their other benefits, cabinet bases can also further elevate and seal cabinets from water incursion from the duct system. Using civils elements for installations that allow rapid installation or replacement of equipment future-proof the non-technology elements of an installation, such as mounting EV chargers in retention sockets, means in the event of damage or upgrades being required, these can be achieved much more quickly. This also lowers the carbon requirements for works, gets rid of those civils elements when updates are made. In cold and damp environments, it's been common to fit cabinet heaters. However, in hot climates, whilst Peltier coolers and fans offer an active measure to stop equipment from overheating, using additional cabinet shades can overcome a lot of these issues in a passive way. This is a traffic signal controller installed in Bangkok under a police shade. In extreme cases, some cabinets have even been placed in air-conditioned booths. Screens on cabinets and structures provide shaded space with air circulation, and planting around installations can provide protection from the sun and from dust storms, although it obviously poses an issue if there is a risk of bushfires occurring. Although we do look at issues such as wind loading, extremes in weather may lead to a need to further strengthen structures. So should we be analysing if there is any need to have these items of equipment on the roadside any longer? To protect against lightning damage, suppliers have added protective devices to stop equipment being damaged like this. However, using underground duct runs would have minimised the incidence of strikes affecting installations in the first place. With advances in battery technologies and micro uninterruptible power supplies, it should be possible to protect the operation of systems much more easily if main supplies are interrupted. However, this can be taken further by using distributed renewable energy generation to provide an alternative to using or relying on mains electricity. Mesh-type wireless communications will also provide a solution to maintain connectivity if individual nodes go down, because the communications include redundancy and alternative routing through the network. I hope you found that interesting. We've got many more episodes coming up, so make sure that you click on the like and subscribe button so you don't miss out on anything. Until then, see you next time.